Okay. In this mod, we're going to take the electrons or the charged particles and we're going to put them to work for us to get some kinetic energy, and that will give us work that we need for our appliances and our lives. So, we are going to start with some definitions. If you would, draw this picture where you have a little box where there's a chemical on one side and a chemical on the other. Draw that on your notes and we'll talk about that. And the chemical on top wants to lose electrons, and the chemical on the bottom wants to gain it. So if you would just give me a quick sketch of that, and I'd be so pleased. That's what we do a lot of the times. This is a barrier through which this chemical cannot pass. So we have the chemical up top that wants to lose electrons and the chemical below that wants to gain electrons. So then all we do is we have a little trick. We take a conductive material and we hook one to the other, and guess what happens? As you can foresee, there's going to be a flow of those extra electrons. The chemical that wants to lose its electrons is going to send it down the path and to the chemical that wants to gain electrons. So this must be a conductive material through which electrons or charged particles will flow. And we call that an electric circuit. So when we see an electric circuit, we know the charged particles are moving through it. What is this that I have drawn? Do you recognize it? This is the theory behind one. Do you know what that is? Where's my purse? I'll bring it. I have to get one to show you.
A battery?
What do you think it is?
A battery?
Yeah.
That's what I was.
But we're going to see if, oh, maybe I threw my battery in here. Let me see. I brought a battery and a conductive material. So what's going to happen?
You're going to put it on.
Yeah.
Get hot.
Yeah, let's see. This might be a dead battery. I'll find out quickly. Kind of dead. Usually it like burns. Let's see if I have another battery floating around. See if you feel anything. Maybe I'm like Zach, I'm immune to it.
It's a little hot, but
Do you think it is?
Not really.
It's getting warm.
Yeah.
So if you could hold that and don't burn yourself. But when it gets a little bit warm, pass it to the next person. I'll see if I have another battery.
I mean, it's not warm enough to like make marshmallow, but just casually just have a whiz on your face.
But wait till like the class is over and I'm just walking around the school.
Ooh, it's hot.
He's not
It's hot.
What?
He doesn't move.
I mean,
right.
if he wants to, he will, but I'm
Gonna
warm
do it?
right now and he's cold, so
He's cold.
It's hot.
he's not.
Careful. It's actually not. You have to touch the battery. You feel the hotness.
Oh yeah, dang.
Feel any warmth, Brian?
Yes.
Do you? So it is working. Just touch the battery. It's getting pretty warm. Okay, well, all right, pass it around, Brian, so everyone can feel the burn.
Yeah, feel the burn.
I wish you. Why did she change that?
Dude, it's hot bricks right now, yo.
Is it getting really hot?
Yeah. Ooh.
All right, well, don't burn yourself.
Dude, it's cool. Touch it. Squeeze the side.
In-
I haven't burned my hot glue gun. It's not that hot.
Some people have a high
Crafting
tolerance
props.
to heat.
Be like, I got burn immunity.
No, it sucks though, because one time it dripped like right here. I was screaming.
We can warm Toby up real quick.
Oh,
Okay,
Toby.
then, okay.
Okay. Is it still getting warm? It'll probably continue unless that battery's probably near dead, so that's pretty warm.
Yeah, that is.
It is really warm. It's like toasty.
Yeah.
It's cool how it does that.
All right.
Do you want it?
Very good.
Awesome. I'm gonna do that at home. Like, absolutely bored. Power goes out. You guys want to do it?
Okay. So what we have
This is
here,
what
It's
was
great.
Coca.
If you're cold in your house and the power goes out, you just grab that.
we have electrons running through a circuit. We have proof of it because we can feel the burn as it goes through. All right. So please indicate on your notes that this is nothing more than a battery. So, what happens to, what do we call it, when all of the electrons run through, all the excess electrons? What do we call that? What do we have remaining when all the excess electrons run through to where they're needed and there's no more? What do we call that? Dead battery, right. That's probably what I almost have there, so. All right. If you notice on this battery, and any battery, they rate them. Do you know what they rate them with? Have you looked at your batteries lately? Not the AA and the D, but what's another rating you see on here?
FDA approved, Steve?
Yeah, probably. But I'm talking about another measurement. See if you can volts. Volts, right. So this one says 1.5 volts. So a measure of electric potential is volts. The word electrical potential could best be realized by thinking of it in terms of water. Suppose we had water in a hose, and that hose is hooked up to a tank, and we pressurize the water in the tank. We put a whole lot of pressure in the water, in the tank. So when you turn on the hose, you get a lot more water per second. So this is, voltage is like pressure. It's electrical pressure though. So, but I visualize it, all my electricity I visualize with water. So it helps my brain to obtain it. So in plumbing, voltage would be like water pressure. So if anyone have water pressure problems at their house, you go to rinse your hair and you have drip, drip,
Only
drip.
like
All right.
everybody else.
All right, so if we were transferring that idea to electricity, you would have a low voltage. There's not a lot of pressure pushing those electrons through. So keep that in mind when we talk about voltage. The unit for voltage is the volt. So we'll call this voltage, and this is volts, whatever. It's volts, measure volts. So volts are in the unit of volts. We use the V to indicate that. So the more voltage means there's more current flow and more kinetic energy, which we use for more work. So usually more voltage is a good thing. So now let's talk about the next one. Away from pressure, sometimes we just want to know how many particles are there. So the actual charge amount, how many charged particles are in our circuit. So we're going to count them through a circuit per second. So that kind of measurement is called current. And it is indicated with the letter I. I'm sorry, that's where I don't know, I guess physicists can't spell current. So it's measured, this is in V, the abbreviation is V. The abbreviation for current is I, and it's measured in amps. So amps, when someone tells you the amperage you have, it's how much current is running per second, different than the pressure voltage. And the last idea we have to meet is the amount of friction in the conductor, and that is resistance. All our conductors, no matter how good they are, have some resistance because there are atoms in it. So even though this turned out to be a pretty good conductor, this tin foil, it's still made of atoms. So when our electric particles try to flow through it, they're going to bump. That's why we get the friction and the heat that you felt. So resistance is amount of friction in the conductor. So sometimes we want a lot of resistance and sometimes we want to reduce the resistance. R is the symbol for resistance, and we will measure it in ohms. And ohms is this symbol. It looks like an upside down horseshoe with legs. What's that? Greek. What is it?
Omega.
Omega. Okay, so we have omega. is the symbol for ohms. Amps and voltage.
So is R and omega interchangeable?
Well, R is in a formula. If we want R, we would put R. In the formula, if we want resistance, we would put R. But at the end, we would give it in the unit of ohms.
Okay.
So you'll see as we go. There's a formula that relates these three, and is one you've probably seen before, and that is voltage. Pretty important, I'll put it up top. Voltage equals IR, Burr. Have you seen that one before somewhere? No? I'm not sure what your electrical past has been. If you've had any, you've had this. So voltage is the product of current flow times resistance, V equals IR. So as electrons move, the kinetic energy is what we're looking for, but the bumping around is caused by hitting atoms in the conductive material causing resistance. It all works together in that way. So let's see if we can think of, before I give you a problem, which is coming up, let's talk about resistance just a little more, and that is what would cause a lot of resistance and what would cause a little resistance. So if we have a material that is wide conductor, and if we have a conductor that is narrow, that will affect our resistance. So which is which, do you suppose? MK, do you think the wide would give more resistance or the narrow? Actually, because there are a bunch more electrons